Exercise 1621 is asking you how you would use an H1-NMR spectrum to distinguish between two compounds. And so what you'd want to do is you'd want to look at the four different pieces of information that you would get from an NMR spectrum, and you'd see how one of those would be different in the two compounds. Now you'll work your way down. First check the number of signals, and if those tie, then look at the location of the signals. If those tie, look at the area. If that ties, look at the shape. But if it doesn't tie somewhere up here, then you don't have to consider the other four factors. If the number of signals is different, then that will tell the molecules apart. So here you're just looking at each of these four factors one at a time. So here we have these two molecules. Let's draw all of the hydrogens in so we can be more precise when we're talking about them. And what we'll look for are the different electronic environments, because that is what's going to give rise to the different number of signals. Okay, well, in the molecule on the left, you'll notice that there is a line of symmetry right down the middle here. So that means everything on either side of that line is going to be in the same electronic environment. So for example, these hydrogens here are in the same electronic environment. They're both one away from a carbonyl and one away from a benzene ring. And so the hydrogens that match it on the opposite side of the symmetry are in the same environment. That's what it means to have symmetry. Everything surrounding those is the same. And next, this hydrogen here is close to that five-membered ring, and the thing on the opposite side of the line of symmetry is also has the same stuff surrounding it. And last, these hydrogens here, that's even further from the five-membered ring, and so from the carbonyl. So that's a new electronic environment. And the thing on the opposite side of the line of symmetry, that hydrogen is in the same electronic environment, so that would be another signal. So here we would have 1, 2, 3 signals. Okay, and the molecule on the right does not have symmetry. There's no symmetry there, and so when we think about the electronic environments, each group of hydrogen is going to be in a different one. So those two hydrogens are right next door to carbonyl. That's different from being 2 carbons away from the carbonyl, which is different from being 3 carbons away from the carbonyl, which is different from being 4 carbons away from the carbonyl. And then you get close to it on the other side, but it's surrounded by different stuff, and yet again, surrounded by different stuff. So here, this molecule would have 1, 2, 3, 4, 5, and 6 different signals. 6 different signals. And so that is because these two molecules, so we'll separate those in our mind, because these two molecules have different numbers of signals, six different types of shadows that are going to be cast when you shine radio waves on them in a magnetic field. That's how you can tell them apart. So you don't even need to tell. I mean, they'll have different locations of the signals, different areas maybe, and different shapes depending on the splitting. But the truth is, you could just use the number of signals to tell these two apart, and that would be enough. So we found this first factor. We could just use the number of signals to tell those two apart. One of them would have 3, and the other would have 6. So you would want to, in the answer to this, you would want to identify the factor, and you'd want to identify how you can use that factor to tell them apart. So you'd have to say specifically, the molecule on the left would have 3 signals, the molecule on the right would have 6 signals, so we can use the number of signals to tell the molecules apart. All right, let's try the same thing with this one. So first we'll draw in all of those hydrogens. Oops. Okay, and a line just to separate these two molecules in our minds. So the molecule on the left, first you have these hydrogens. You have those hydrogens there that are alpha to the carbonyl, and really to the rest of the whole molecule. So that's going to be one signal. The next time you run into hydrogens, they all happen to be in the same environment. So notice all of these hydrogens are actually in the same environment, and the reason why is because for all of them, you'll just go 1, 2 atoms away from the ester. They're all the same distance away from the same groups. That's what it means to be in the same electronic environment. So all of those will just show up as a second signal, so that'll be a total of 2 signals that we get in this molecule. If you compare that with this next one, and I'll use 2 different colors too, so we don't mix them up. These hydrogens are in one environment. It's our first electronic environment. They're alpha to an ester. And then on the other side, all of these hydrogens are in the same electronic environment. Now, not as the blue ones, they're in the same electronic environment as each other, because they're all 1, 2, 1. They're all the same distance away from the rest of the molecule. And so they're surrounded by the same stuff. They're the same distance away from the same stuff, so they're all in the same electronic environment. So that would be our second signal. So in both of these molecules, you get 2 signals. So we can't use the number of signals to tell the molecules apart. So let's look at the second factor, the location of the signals. In the left molecule, these yellow hydrogens that's a CH3, and so normally you'd expect a CH3 to show up at 0.9. This is coming from those tables that we used in a previous problem, tables that had listings for the different chemical shifts. So these tables right here. So you'd want to refer to those tables. You can see CH3 would have 0.9. I won't include the tables in this video. You have them in previous videos. By this point in these exercises, you would want to have these memorized. So if you don't have them memorized, you can take a screenshot and include that to the side of the video so it's easier to follow along. I would encourage you to memorize those before you attempt these problems. Okay, so those would show up at 0.9. The brown ones are also CH3, so you'd also expect those to show up at around 0.9. But you have to adjust those values based on the electronegative stuff nearby. The yellow hydrogens are alpha to a carbonyl. Here's your carbonyl. Right next to it, that's the alpha position. So they're alpha to a carbonyl, and if you're alpha to a carbonyl, then you add 1. Oops, sorry. It's supposed to go with that other one. So you'd add 1. And so really you'd expect those peaks the peak for those yellow hydrogens to show up at 1.9 parts per million. So let me erase the number of peaks here so that those don't get confusing. For the brown hydrogens, those are also CH3s, so we expect them to show up at 0.9. But those are alpha to an ester. So if you notice on this other side, this is the ester side of this. So it's going to feel an effect from both of these oxygens. And so you add 3 to that, and that's coming from those tables that we saw a second ago. So we'd really expect the signal for those hydrogens to show up at 3.9. So we're looking at 2 signals. We would expect a signal at 1.9 and a signal at 3.9. All right, next. These hydrogens here, those are CH3, so we'd expect them to show up at around 0.9. And the purple hydrogens, also CH3s, so we'd expect them to show up at around 0.9. And again, those values are coming from those tables for the shifts. All right, now we have to think about the electronegative stuff nearby. The blue hydrogens are alpha to an ester. So notice the esters there, they're 1 atom away from that ester group, so you'd add 3. So we have 3.9. The other hydrogens, the purple ones, those are alpha and beta. And so if you're beta from a carbonyl, then you add 1/5 of 1, which is 0.2, and so we'd expect that to show up at 1.1. And I apologize, now that I look back at this, I had the wrong number here. Forgive me. These hydrogens are not alpha to this ester. Here's our ester. The alpha position is right here, but they're not on that. They're on the beta position, so I apologize for that confusion. If you're beta to an ester, then you add a 1/5 of 3, which is 0.6. So that would show up at 1.5. So sorry about that little error. This methyl group is alpha to a carbonyl, so we added 1. These hydrogens are beta to an ester, so we added 0.6. These are alpha to an ester, so we added 3. And these are beta to a carbonyl, so we added 0.2. Okay, so we're expecting the signals in the molecule on the left to show up at 1.9 and 1.5, and in the molecule on the right to show up at 3.9 and 1.1. And so you can use the second factor, the location of the signals, to tell the difference between these two molecules. And you wouldn't just want to say, you can use the location of the signals, you would want to say where those locations would be to justify your assertion that you can tell the difference between the molecules based on the location of the signals. Okay, for C, first we'll draw the hydrogens in. Okay, so we'll keep these separate in our minds, and we're going to look at the first factor, just the number of signals. How many different electronic environments are there in these molecules? You'll notice that both of the molecules have a plane of symmetry going down the center. So everything to the left and right of that plane of symmetry will be in the same electronic environment. So for example, these hydrogens that are right next door to the ether, that's one electronic environment. And the things on the opposite side of the plane of symmetry will be in that same electronic environment. So those will represent one signal altogether. For the next ones, these hydrogens are 2 away from the ether, so that's a different electronic environment. And the hydrogens on the opposite side of that plane of symmetry, those are in that same electronic environment, so those will be 2. So we have those 2 signals in that molecule on the left. Molecule on the right, hydrogen's right next door to the oxygen, so that's 1 signal. On the other side of the plane of symmetry, that's going to be part of that same signal, so that's going to be 1 signal. Hydrogen's 2 atoms away from the oxygen are a second signal. And then you have hydrogens that are three atoms away from the oxygen, and so that would be your third signal. So because there are different numbers of signals in for these 2 structures that we get, that's enough to tell them apart. So you could say, how can you tell these 2 molecules apart using NMR? Well, the molecule on the left would have 2 signals, the molecule on the right would have 3 signals, and you would want to show your work to justify that statement. For the next one, first let's draw in all of the hydrogens. Okay, so we'll think about these separately. Let's identify all of the different electronic environments in the molecules. Now on the left there's no plane of symmetry, but on the right, the molecule on the right, there's a plane of symmetry sort of going diagonally. So first thing we want to do is figure out how many signals we'd have in each of these and whether that ties. In the molecule on the left, you have a hydrogen on an oxygen. That's one electronic environment, so that's one signal that you get from that. Going clockwise, you have a hydrogen that's in between an alcohol and a chlorine, so that's a second signal. Then you have a hydrogen on the other side of the chlorine. It's a third signal, third environment. You have a hydrogen even further, so 2 atoms away from the alcohol and the chlorine. It's a different electronic environment. So that's your fourth signal, and then you would have this last hydrogen here, which is right next to the alcohol and far from the chlorine. That's your fifth electronic environment, so your fifth signal. So 5 signals in the molecule on the left. For the molecule on the right, because of the symmetry, you would end up having the hydrogen on the oxygen, so that's definitely one signal. For the one next door to it, this hydrogen, that's right next door to the alcohol and further from the chlorine, so that's a different electronic environment. But across the plane of symmetry, that other hydrogen will be in that same electronic environment, so that's a second signal. The third hydrogen is closer to the chlorine, further from the alcohol. That's a new electronic environment, so a new signal. The hydrogen on the opposite side of the plane of symmetry is in that same environment, so that's a third signal. And so the molecule on the right would just have 3 signals in its NMR spectrum. 3 peaks or shadows. And so you can use the number of signals here to tell the molecules apart. The molecule on the left will have 5 signals, and the NMR spectrum for the molecule on the right would only have 3. And if you were ever in doubt, you could use the other factors to confirm that. Like if a lot hinged on you telling these two apart, and you were presenting your findings to a journal, or you wanted to publish them in a journal, or you were presenting it to a board to decide whether they wanted to continue with the research you're proposing, or if they want to fund further trials with the molecule you're interested in. Of course, you'd want to go through these other factors, but if you're just looking for yourself, you can use the number of signals to tell these two apart. All right, same thing. Let's fill in the hydrogens. Okay, molecule on the left. You'll notice that in the molecule on the left there's symmetry. There's a line of symmetry, a plane of symmetry going down the center. And that is not true for the molecule on the right. So on the left, these hydrogens at the top, those are in the same electronic environment, so that will be one signal. And the other hydrogens, those are all in the same electronic environment. One atom away from a carbon and double bond. The hydrogens on the other side of the plane of symmetry are in that same electronic environment, so you'd only have a total of 2 signals in the NMR spectrum for that molecule. For the molecule on the right, there is no plane of symmetry, and so you would have this hydrogen here, that's in one electronic environment. The one in the methyl group coming off of the ring, these 3 hydrogens there, that's a different electronic environment. The hydrogen attached to the ring, but not to an atom in a double bond, that is a third electronic environment. And the hydrogens on a methyl group that is not attached to an atom in a double bond, so notice this methyl group is attached, this methyl group is attached to an atom in a double bond, this methyl group is not, so it's a different electronic environment. That would be our 4th electronic environment. So in this molecule, you'd have 4 signals in its NMR spectrum. And so you would be able to use the number of signals to tell these two molecules apart. The molecule on the left would have 2 signals in its spectrum, and the molecule on the right would have 4. And so you would want to show your work for this by circling or separating and labeling the different electronic environments, showing the exact numbers, and then mentioning that you can use the number of signals to tell the 2 molecules apart. Okay, finally, let's draw the hydrogens in on this last one. Okay, so we'll look at these separately. Now, there are actually 2 planes of symmetry in the molecule on the left. You have one going down, and you also have one going across. So, if we take one group of hydrogens, that's an electronic environment, to be in that methyl group there, but everything across the vertical plane of symmetry is in the same environment. And everything across the horizontal plane of symmetry is also in the same environment. And if we choose one of those, everything across the vertical plane of symmetry to that is also in the same environment, and so there's only one electronic environment in this whole molecule. This would only have one signal, one peak in its NMR spectrum. There is also a plane of symmetry in the molecule on the right, but there is only one. That's that right there. And so here you would have these hydrogens. That's an electronic environment with a methyl group. That is in the same plane as that's the same electronic environment as the hydrogens that are in the other methyl group. And actually, they're also in the same environment as these last hydrogens. So you could actually think of having another plane of symmetry right there, going vertically down here. Another way to think of it is everything here is 1 atom or 2 atoms away from that center carbon. So it all is the same distance away from the same stuff, so it's the same electronic environment. So those are actually all just one signal. It's the other hydrogen, the hydrogen that's all by itself, that is in a different electronic environment. So we have 2 different electronic environments here, so you'd have 2 signals in that NMR spectrum, or in the NMR spectrum for that molecule. So you'd be able to use the number of signals to tell these 2 apart. You'd want to show the planes of symmetry and label the different electronic environments and the number of signals in each of the molecules. And once you have those labeled, you would just say, you can tell the molecules apart because they would have different numbers of signals in the NMR spectrum. So that's how you can use NMR to tell molecules apart. If you have the molecule you're interested in narrowed down already, and you know it's one of a few different things, you can use NMR to tell pretty quickly, without doing too much complicated analysis, which of the molecules you're interested in, your real